recipe. I'll send you my favorite recipe. Okay, so exam 1 is on Friday. And the topics are everything up through strain and constitutive relationship. And I talked about how you get the Young's modulus and the Poisson's ratio, and those come from doing a tensile test of the material. But I want to talk a little bit more about what happens when you take a tensile test. So if you cut out a small, thin sample of a material and you clamp it at both ends and you pull on it and you keep pulling on it, at first you're going to get an elastic deformation of the material. That means for a while you'll stretch it and it's going to be, barely or not visible to your bare eye, but you'll stretch it somewhat, and if you let go of the load, it would return right back to its original shape. So that's what happens at the beginning. And during that time, there is a linear relationship between the stress and the strain. So let's think about what this would look like if you plotted a stress versus strain graph. Okay, so we'll make stress on the vertical axis and strain on the horizontal axis. What's the strain before you apply any load to the material? 0. You should always answer the easy question first, and now, like, he's already answered his question, and now the rest of you have to answer the hard questions. Yeah, he doesn't. He's just here for the donuts, for the free donuts. P.S. No free donuts. I don't have any. Okay, so think about what happens now during, all we care about is the range of linear elasticity. There's a linear relationship between stress and strain. So what does the stress versus strain graph look like during that, in that region of the deformation? Yeah, it's a line. It has a positive slope, because if you increase the load, you increase the deformation. And so you get something like that. And that is the part okay, so this is the part that is relevant to this class. This is the linear elastic region. Everything that we're doing in this class takes place in this region of the stress-strain curve. But this isn't the point where the material breaks in two. Okay. For a very, very brittle material, that's not too far from the case. If you're doing this with diamond or something, or any kind of ceramic, that is in the ballpark of where the thing breaks. But for metals, a lot of stuff happens between the region that we're doing calculations for and where the thing comes into two pieces. By the way, what does elastic mean? Yeah, so elastic, I think, like think about your underoos. Okay? Like what makes the waistband in your underoos elastic? What is it about? So yeah, I think it a lot of people would say it's the stretchiness, but you could make the waistband of your underoos out of Play-Doh and they would still stretch. They would just fall down when you let go of them because, and that's not ideal. Um, because you'd stretch them out to put them on and then they wouldn't spring back. So the thing that makes something elastic is that when you remove the load, it returns to its original shape. Okay? So Play-Doh, even though it's stretchy, it's not elastic. It's plastic because if you smush it like this and let go, it stays exactly like that. Okay. So in this region, as soon as you let go of whatever you're doing to it, and it can be a complicated mix of things, you can have a shear stress on it and be twisting it and compressing it, but you let go of it, it returns to its original shape. After this, it starts to undergo a plastic deformation, and it usually starts out something like that. So initially, it just starts to become a little nonlinear. You know, um, from this point on, all the deformation is permanent. So that's a plastic deformation. Remember that superhero Plastic Man? That was a bad name, or else every time he stretched, he would stay that stretched. Um, and then it does some weird stuff. Uh, like this. And then there finally is um, this is what do we call that? I guess that's just the pure failure. Um, there's this weird stuff that happens here where what's going on is that slope gets smaller. Is that material getting more or less stiff? So think about like the slope of this, okay? The slope of the linear region. Um, that is the stiffness of the material. This slope is Young's modulus. If you have a really stiff material, this is tilted more this way. If you have a really flimsy material, it's like this. And so it starts out with a high stiffness before, relatively high stiffness before the slope starts to drop. And so it's getting weaker at this point. It's getting flimsier. As soon as the permanent deformation starts, it's becoming easier to stretch this. And it gets easier and easier until applying the same, without increasing the load anymore, it's just starting to stretch. Okay, that's what's going on here. But then around here somewhere, this weird thing happens. It's called strain hardening. And so from this point on, the material actually starts to get stiffer again. Um, No, that is, I don't remember molecularly what happens to make strain hardening happen, but it's just some kind of molecular phenomenon that makes it start to get stiffer again. But I mean, you could think of this thing as just being stretched. So there's the same amount of shearing happening through the whole thing. If you think of, so if you're just stretching this, it's in uniaxial tension. And if you, well, since it only has tension along one axis, it's already in its principal coordinate system, right? And so then based on the principal stresses, you could figure out rotated at 45 degrees from here would be the maximum shear stress. And so it's in shear stress the whole time. And if it was a brittle material, it would break along a 45-degree angle like that. So what happens here just has to do with what's going on with the atoms and something weird happens there. There is one other thing I want to talk about with this, and that is that somewhere around here, there are two different ways you could think about what's happening. The solid line is is what you get if you're calculating strain the way we calculate strain. And that's called engineering strain. That's using our formulas for strain. But this dashed curve comes from calculating the true strain. So let me talk about the difference between those two. So engineering strain versus true strain. Okay, so as the material is stretched, Poisson's effect causes the material to contract along the off axes. Okay, so as this gets longer, if you measured like this distance, it would get smaller. The more it contracts along those dimensions, along those directions, the smaller the cross-sectional area is in the, I guess, in the, yeah, how do I, so let me draw this picture. So if it starts out like this, and this is the area A, the stress is equal to the force divided by that area A, right? if you stretch it, let me call this A2, and that A2 is going to be less than the original A. And so as that A2 gets smaller, the true stress is equal to the force over A2. And so if the loads are all the same, but in this you're calculating the stress, and I said true strain and engineering strain. People talk about the strain, the true strain and true stress, engineering strain and engineering stress. But if you have the same amount of force in both of these two cases, but for the engineering strain you're dividing by that big original area, and here you're dividing by the smaller actual current area, you just get a bigger value of the stress in that way. And it starts to get really exaggerated when the material starts necking, it's called. I guess it gets exaggerated. Starts to experience necking.
Isn't that an old term for making out?
Yes, I don't know if it's old, but it is a term for that. But that's not what it's experiencing. I'm sorry to say for its sake. What it's experiencing is, it starts to get like a shape like that, where it starts to identify the part where the breaking is going to occur. This is long, long after the elastic region, but this is the neck. Now at this point, you know that when it breaks in two pieces, it's not going to be here or here. It's going to be somewhere in this region. And you can see that now you have a huge difference in the cross-sectional area between the place where the fracture is going to occur and, the original area. And that's where the engineering strain, engineering stress, and the true stress and strain start to diverge a lot. So over the whole thing, there's some small amount of difference between the engineering calculation and the true calculation. But it starts to get really noticeable once you get well into that plastic deformation. And that's here. Okay, that's where the necking is starting to happen. Okay, so when you do a tensile test, you come out with a readout like this. All of this stuff is used for calculations involving plasticity. But for the stuff that we care about in this class, all we care about is this. This circled region, we get the stress and strain calculations. We use those to get a best fit for the slope. That's our Young's modulus. We measure the strain along this axis or along the axis going into the page. And those we use for the Poisson's ratio. And then from those, we get the compliance or the stiffness matrix. Any questions about that? say one more thing. So now we're kind of done with the setup for this class. Most of the rest of the semester, what we're going to be doing is trying to figure out how to go from a certain object under a certain configuration of loads to figuring out what the stresses are inside that object. Okay. In every case from now on, we're also going to calculate the strains using the techniques we've talked about, calculate the maximum normal stresses, maximum shear stresses and stuff. But essentially from now on, we'll just be learning how loading configurations relate to stresses. And there's one tool that's going to be really important for us. And this isn't really a mathematical thing. It's a experimental thing, a fact that people have noticed. It's called Saint-Venant's principle. Saint-Venant is like a French name, some French guy. And Saint-Venant's principle says in an actual in a stress strain problem, you can replace the actual loads with an equivalent system of loads as long as you're far enough away from the loaded surface. Okay, so that means that, for example, if you have a beam and it's being loaded with a point force this way and a point force this way, call those both F. This, calculating the stresses and strains in this would be hard to do. To really like rigorously figure out what the stresses and strains would be, where, I mean, you can imagine this being made out of silly putty, you know, what's going to happen with the deformations? You get a giant deformation at the point where this load's applied and a giant one there. That would sort of pull out like this, and then you'd have weird stress concentrations near that, right? We can do calculations for a beam like this, you know, the same beam, Now instead of being point loads, we have uniform distributed loads that add up to F. So this is relatively easy, this is relatively hard. But Saint-Venant's principle says, as long as we don't use our calculations close to these two loaded surfaces, the results we get for this are the same as the results that would occur here. So essentially, we're just going to throw away our results near the loaded surfaces. And everything that we haven't, all the results that we haven't thrown away, all the stuff that's still white, we're going to trust the results we get here to represent what's going to happen here. Okay, that's an experimental result. And there is sort of a rule of thumb for how far away. Yeah, any questions? You understand the idea on that? So here's sort of a good rule of thumb. Again, this isn't like a mathematical, this isn't a mathematical fact. This is just something that people have found to hold most of the time. So you should be at least as far away from the loaded surface as the longest dimension of the loaded surface. Okay, so if this is if the cross section of this is circular, then take the diameter of that circle, because the loaded surface is the cross section there, that circular shape, and then go at least the diameter of that circle away from the end. If that's a square, take that long diagonal of the square, go at least as far away as that diagonal. And that means that, if what you need for your engineering calculation is to know what's happening inside these shaded regions, there's nothing you can do with our techniques to find that out. Okay, there's crazy stuff going on inside there, and we don't have any way of calculating that. But if you're lucky and the stuff that you really want to know is what's happening overall in the main body, then this we can feel confident about even after we make that simplification. Any questions about that? All right, so what if what you need is information near the loaded surfaces? Well, in that case, you have to use, well, you could do, use more advanced mathematical techniques, use the same ideas, but for the most part, what people would use is finite element analysis. You'd use numerical software to do the calculations in those regions where the stresses and strains are changing really quickly as you go from one spot to another. So finite element analysis, people call that FEA, finite element analysis, or FEM for finite element method. Those are the same thing. Still, in cases like that, this overall approach a lot of times is helpful because you can feel more confident about your finite element results if over the rest of the region that where you do trust your hand calculations, if the finite element results roughly match your hand calculations in that region. Okay. Any questions? All right. So now we're going to start talking about stresses in like how to go from a loaded, physical finite size thing to calculating the stresses and strains inside. We're going to start with the simplest case, and that's objects loaded according to the rules of stress elements. So some examples would be, a stress element is infinitesimally small. It's a cube. But if you have a material that's loaded here and here, and let's say these are distributed loads, and they're also loaded with distributed loads here and here, and then on the back side, like that, and under like that. Okay. The tractions on these faces have all of the relationships that you would require for the stress element. You have equal and opposite forces. So the total force applied on the negative x face is the same as the total force applied on the positive x face. The shear tractions on these faces have all of the relationships they need to have. This traction is opposite this traction. This one's opposite this one. This one and this one have the right direction and the right magnitude relationship. Let me call that, I'll call that S for shear. And so when you have that, you can just calculate the tractions on those faces, and those are going to be the tractions on the faces of the stress element. The tractions on the stress element faces are the tractions on the faces of the object. Okay, so in this case, what if instead of this being a distributed load, this was a point force with a magnitude of S? Okay, so there's like a point force acting right at this point here, pushing it that way. And here there's same thing, like there's a point force over here. It all depends on the dimensions of the thing that you're looking at. In this case, this loaded face is pretty big, and you can't, like if you think about the longest dimension of this loaded face, there's no way to get this far away from that face and still be on this body. Okay, so in that case, in the case of these shear stresses here, Saint-Venant's principle wouldn't help you at all. You would never be able to trust, you would never be able to, if this was loaded with point forces, this face and this face, there's nowhere on the body where you would be able to treat it like it was a uniform distributed load and trust your results. Okay, but the loads here and here, you could trust, you know, somewhere in here there's like a little window where you could trust those results if this was a point force or this was a point force, because the longest dimension of that face is smaller than the length of this thing. Okay. Okay, so let me do an example. Let's say that we have a circular cylinder the length is 0.1 meters. We have a uniform distributed load on the top of 5,000 newtons. And same thing on the bottom. And let's say that the radius of this circle is 1 centimeter, 0.01 meters. And we want to know what's the stress tensor for points inside this body. Well, if I use a coordinate system like this, the only loads that we have are, or the only tractions we have are normal tractions in compression on the y and the negative y face. And so sigma yy is equal to negative 5,000 divided by the cross-sectional area of that face, which is pi times 0.01 squared. And where did that negative come from? Yeah, on the positive y face, it's in the negative y direction, or you could just think of it as compression. And so this gives you negative 1.59 times 10 to the 7 pascals. And so the stress tensor is zeros everywhere except YY position, which is negative 1.59 times 10 to the 7. Any questions about that? And what if that What if that wasn't originally a distributed load, it was a point force? Well, in this case, you have a long, slender thing. You're not throwing away a very high percentage of this material to ignore the two endpoints. So just go one diameter away from the end, and everything from here to here, you trust those results.